This screencast provides additional resources to help students understand how the state of the feed to a distillation column impacts the vapor and liquid flow rates inside of the column. In general, we are interested in graphically determining the number of stages required to achieve a desired separation, given the feed conditions, such as composition, temperature, and pressure, and also the operating conditions of the column, chiefly pressure and reflux ratio. To start, we will investigate a binary system using the McCabe-Thiele technique, in which the constant molar overflow assumption is valid. Above and below the feed, the liquid and vapor flow rates will be constant, even though the composition will change. A mass balance on the column above the feed tray yields the operating line, which will be a straight line with the slope of R over R plus 1, where R is the reflux ratio. Similarly, a mass balance on the column below the feed tray yields a second operating line. The slope of each operating line is equal to L over V, where L is the molar flow rate of the liquid and V is the molar flow rate of the vapor. The two operating lines meet at the feed, and the slope of the feed line depends on the state of the feed. If the feed comes into the column as a saturated liquid, all of the feed will flow down the column, augmenting the liquid flow rate in the column. Lm equals Ln plus F. The vapor flow rate will not change above and below the feed. Vm equals Vn. If the feed comes into the column as a saturated vapor, all the feed will flow up the column. The liquid flow rate will not change. Q can be defined in terms of enthalpy, or it can be defined as the increase in the liquid flow rate below the feed tray due to the feed per mole of feed. For a saturated liquid, Q has a numeric value of 1, and for a saturated vapor, Q equals 0. The slope of the Q line is equal to Q over the quantity Q minus 1. In this dynamic simulation, the feed starts as a saturated liquid, with the arrows showing that all the feed flows down the column, increasing the molar flow rate of the liquid below the feed compared to that above the feed. Q is equal to 1, and the slope of the Q line is infinite, giving us a vertical line on an XY diagram. As I move the slider, the feed is changed from saturated liquid to two-phase, with some liquid and some vapor. The arrows show that the liquid flows down and the vapor flows up the column. For Q equals 0.5, half the feed flows down the column and half flows up the column. As a fraction of vapor in the feed increases, Q decreases until the value reaches 0, at which point the feed is a saturated vapor. The slope of the Q line is equal to 0, and the Q line is horizontal on an XY diagram. If the feed is superheated, the feed brings additional energy to the column and must be cooled to the feed tray temperature. A superheated feed will cause some of the internal contents of the column to vaporize, with the heat required for vaporization coming from the superheated feed, allowing the feed to come to the tray temperature. For a superheated vapor, Q is less than 0, and the slope of the Q line is positive. Finally, the last case is for a subcooled feed. In this situation, the feed is at a lower temperature than the feed tray and must be heated up to the feed tray temperature. The energy required to heat up the subcooled feed comes from condensation of some of the vapor in the column. As you can see by the arrows, this results in an increase in the liquid flow rate below the feed that is actually larger than that contributed solely by the feed. The value of Q for a subcooled feed is greater than 1, and the slope of the Q line is positive. This figure shows different feeds and how the Q line varies with the state of the feed. The two operating lines, shown in green and red, intersect at Q equals 0.5, two-phase. In the next chart, the two operating lines intersect at Q equals 0, saturated vapor. Note that for this case, the operating lines are much closer to the equilibrium line, and thus more stages may be required for the given separation. The key takeaway from this screencast is that the state of the feed, subcooled liquid, sat liquid, two-phase, sat vapor, or superheated vapor, plays a critical role in calculating the number of stages for a given separation in distillation. You should experiment with a dynamic simulation and be comfortable sketching where the feed goes depending on the state of the feed.